Hello there my science friends. Welcome back to my channel and Happy New Year! Many of us enjoyed the spectacular fireworks displays that usher in the new year. While I look at fireworks through my chemistry lens, I thought you might be interested to know how much science there is in your colorful firecrackers. So let's finish off your leftover sparkling wine from your New Year celebration and look at the chemistry of fireworks. Let's start with the most obvious and most impressive part of firework chemistry, the colors. Firework colors. The various colors in fireworks stem from a wide range of metal compounds that are used, particularly in form of metal salts, which form an intense color when burned. While the name salt somehow brings up the mental image of table salt, sodium chloride, these metal salts are ionically bonded metal and non-metal atoms. If you want to get a more detailed introduction on this topic, watch my video about fluoride. So which elements are exactly used to produce fireworks with all colors of the rainbow? Let's see. Red is usually produced by the use of strontium salts like strontium nitrate, strontium carbonate or strontium sulfate. Orange can be achieved with calcium salts like calcium carbonate, like the limestone in your kitchen, calcium chloride or calcium sulfate. Yellow, on the other hand, often contains sodium salts like sodium nitrate, sodium oxalate or cryolide. Green fireworks use barium salts like barium nitrate, barium carbonate, barium chloride or barium chlorate. Blue can be produced by using copper salts like copper 1 chloride, copper carbonate or copper oxide. And purple can be achieved by combining the before mentioned copper and strontium compounds just like you would with paint. By the way, some of these colors are notoriously hard to produce. Particularly copper-containing compounds are often unstable at higher temperatures, which makes it really hard to achieve an intense blue-based color. This is the reason why it's often said to judge the quality of a firework by its display of blue and purple colors, as they are the hardest to achieve. But how does the chemistry behind those colors actually work? These metal salts are often covered in gunpowder, which we will discuss in a little bit, to help with the ignition. When the gunpowder combusts, it gives off heat, and this heat manages to excite an electron from the metal atoms to a higher energy level. But these excited states are unstable, so the electron doesn't really want to be there. Instead, they would much rather go back to where they came from, so the electron quickly returns to its original state, also called ground state. And during this process, it gives off the excess energy it initially got from the combustion heat as light. The different metal atoms used have different energy gaps between their ground state and their excited state. And this difference means they emit light of different energy during the relaxation process. Light of different energy is visible to us as different color. Higher energy means smaller wavelengths and colors like blue or violet. Lower energy means higher wavelengths and colors like red, orange or yellow. The big fireworks in the sky, however, are not the only ones that fascinate us at New Year celebrations. Just as spectacular are these little sparklers you can buy in the supermarket. These work in a similar fashion, although instead of using colorful metal salts, they often contain powdered pure metals for a different effect. As well as being important for the production of the little sparkles, those powdered metals in the metal fuel also affect the color of the sparkler. Aluminium, magnesium and titanium all give near brilliant white sparks. Iron, on the other hand, produces orange sparks, whilst ferrotitanium, an iron and titanium alloy, produces yellow gold sparks. Both big fireworks in the sky as well as handheld sparklers have oxidizers mixed into them, and these oxidizers play a very important role. They are often metal nitrates, chlorates or perchlorates, with potassium nitrate being a very common example. When heated, these oxidizer compounds decompose, producing oxygen. The production of gases during the decomposition reaction also forcibly ejects bits of the burning powdered metal from the sparkler. This causes the sparkling effect while they continue to burn and react with oxygen to produce metal oxides. The chlorate and perchlorate ions also function as a chlorine donor, which helps intensify the color of the fireworks. Of course, those metal powders and oxidizers would be useless without a way to bind them together into a paste, which can then be added onto a rod for a sparkler or be formed into a cannonball to be shot up in the sky. For that, a binder is needed to physically hold the chemicals together. A number of chemicals can be used for this, but the most common is dextrin. Dextrin is actually a name used for a group of smaller carbohydrates produced by the breakdown of starch. It can also act as a fuel, although in the amounts used here, doesn't really add much to the pyrotechnics. Believe it or not, water is also required to form this paste, although obviously the fireworks need to be dried before they can be burned. Now, big fireworks are not only spectacular through their display of many colorful effects, but also because of their sound. Firework sounds. The obvious place to start is the bangs of fireworks when they explode into bursts of color. These can be produced simply by compacted gunpowder, also called black powder. It was discovered by chance by Chinese alchemists who were actually much more concerned with discovering the elixir of life than with blowing things up. Regardless, they found that a combination of honey, sulfur and saltpeter, potassium nitrate, would suddenly erupt into a flame upon heating. The combination of sulfur and potassium nitrate was later joined by charcoal in the place of honey. The sulfur and charcoal acts as fuel in the reaction, whilst the potassium nitrate works as an oxidizing agent. Modern black powder has a saltpeter to charcoal to sulfur weight ratio of 75 to 15 to 10, and this ratio has been unchanged since around 1781. The combustion of gunpowder is not at all as simple as it might seem, and doesn't take place as a single reaction, so the products can be rather complicated. The closest thing to a representative equation for the process is shown here, with charcoal referred to by its empirical formula. Alright, so we're getting a good bang out of this. But there's more. Another common sound effect in fireworks displays is the fizzling, crackling sound. These fireworks use a slightly different composition to achieve this effect. Originally, lead tetroxide was one of the compounds used in this composition. But due to the toxicity of lead compounds, in the present day it's more common for compounds like bismuth trioxide and bismuth subcarbonate to be utilized instead. These compounds are mixed with magnesium, an alloy of aluminium and magnesium. The composition is then formed into tiny granules, and when they rapidly combust, they make this crackling effect. This mixture is in the pyrotechnic industry commonly referred to as dragon's eggs. Finally, one of the most common sound effects that accompany fireworks are the screeching whistles when they rise up into the sky. These come from the use of some organic compounds. Various aromatic organic compounds can be used. In the past, salts of the very shock-sensitive picric acid were used, but nowadays gallic acid, salicylic acid and benzoic acid salts are more commonly used. These organic compounds are mixed with oxidizers and then tightly packed into the firework tube. When they burn, the aromatic compounds produce tiny explosions, which cause pressure changes in the gas being ejected by the burning mixture. This creates a standing wave in the tube, which produces the characteristic whistle effect. On a serious note though, as bright and shiny as fireworks seem at a first glance, they do have a dark side. The dark side of fireworks. Without cookies. To onlookers watching fireworks go off, it may seem as if they simply disappear without a trace after delivering their fiery load in the sky. Unfortunately for us and the environment, this isn't the case. Here are the 4 main pollutants fireworks leave behind. 1. Particulate matter. Fireworks produce a lot of very small particles, often referred to as particulate matter PM10 or PM2.5, which can stay suspended in the air for quite some time after the firework display. It therefore significantly increases the concentration of particulate matter in the air. Studies showed that inhaling these sort of particles can have severe effects on your respiratory and cardiovascular system. 2. Metals. As described earlier, metal compounds give fireworks their vibrant colors and can also be present in oxidizers and mixtures. Sadly, these metals tend to persist in the environment. Investigations show increases of toxic metals like lead, chromium and antimony in the atmospheric concentrations in the days following firework displays, particularly around New Year's. 3. Perchlorate. As we've seen earlier, perchlorate compounds are often added as oxidizers to fireworks to help with the combustion and increase the color. Unfortunately, perchlorate can contaminate bodies of water near the fireworks, and elevated concentrations of perchlorate in the water can harm wildlife and human life, particularly when it ends up in our groundwater and therefore consequentially in our drinking water. 4. Pollution gases. Last but not least, fireworks can lead to increases of well-known pollution gases such as nitrogen dioxide, sulfur dioxide, carbon monoxide and carbon dioxide. This can lead to respiratory problems, but can also exacerbate existing health issues like asthma, apart from reacting in the atmosphere and adding to the already existing climate crisis. The stance of global governments on fireworks varies wildly. While some countries ban the sale of fireworks to the broad public, other countries don't regulate this much at all. Personally, I think my dog would love to live in a world without them. But how about you? How are the regulations about fireworks where you live? And what is your personal stance on it? Should they stay or should they go? Let me know in the comments below. I'll see you back in my next video. Until then, I wish you a sciencey start in the new year.